So now that we've had the first lecture, you can sort of see how the class is going to work. The mic is on, right? You can all hear it? Okay, great. So you can see here that if you click the slides for the PDF, they are on D2L, and as long as you're logged in, they'll be visible. The YouTube video is here, and I'm not sure how quickly you watch the YouTube video, but let me just pause it here for a second. I did go ahead and add some timestamps on the bottom. So this will add chapters to the timeline of the video. I'm not going to do that for every single lecture because it does take quite a bit of time, but I find for important videos like the assignments and the intro lecture, or where there's a lot of definitions, I will do that just because it's, it's useful. It doesn't mean that you should skip to like the topics that you think are important. Definitely watch everything, but it's just there. And I wish I could do that on D2L, but there's no mechanism for me to be able to do that there. So there will be timestamps on some of the YouTube videos. Just to give you an idea of what's coming up. So this week of lectures, so today and Thursday, are pretty much all definitions and terminology. It's really dense definition-packed lectures so that we can sort of, after that, we'll go ahead and do the actual fun stuff, which is the programming of the assignments and implementing all this. So then, starting next week, I'll introduce assignment 1, and next week is going to be a lot about assignment 1, how to set up the programming environment, how to use C++. So any worries you have about C++ as the programming language or how to set it up on your computer, don't worry about that. Don't email me any questions yet. I promise you, if the undergrads can do it in my game programming course, hopefully you can also do it as graduate students. So that's sort of what's coming up for the next couple of weeks. So let's get started with the lecture, if this will work. Okay, so lecture number 2, which is the first what I would call testable lecture. Lots of this stuff is really good questions for the exam, so you should definitely know all of this. And not only for the exam, but it's because it's the basis of everything we'll do in the course, right? So you need to have these definitions out of the way in order to do things with concepts involving those definitions. So, as I said before, this is probably the most dense lecture of the course in terms of definitions and terminology. And if you don't get everything right away, don't worry. There's a lot of stuff to understand here, so if some of it kind of glosses over, that's what the lecture slides are there for. You can rewatch the video if you want. And all of these concepts, we'll be talking about them at length throughout the course goes on. And, use those slides as a reference in the course going forward if you're not sure of something. So very first, there's agents and environments. That's what the lecture is titled. And both of those are kind of equally important things. And so what is an agent, at least for the context of this course? Like if you ask a random person on the street what an agent is, they'll probably say it's like a secret agent with the government or something like that. We're not talking about those type of agents, although that type of agent is one of these types of agents, but not vice versa. So an agent is something that exists in a specific environment. And the agent is the entity for which we want to make decisions and take actions. So remember back in the first lecture, AI is essentially making programs or machines that make decisions and solve problems, right? And so the agent is the thing typically that we're trying to make a decision for. Now, not all problems in AI have an agent that like moves around or take actions, for example. Like I gave examples of optical character recognition. Right? There's no little Super Mario running around recognizing the characters. That's not a problem where there is an agent. But in a lot of problems, there is this concept of an agent and an environment, and those are the type of problems we'll be doing in this course. And so in most cases, the environment defines the problem, and the agent is going to give the solution. So when you're asked to solve a problem, you're going to very specifically define the environment in which that exists. And next lecture, we're going to be talking about problems, like how to well define a problem so then we can apply an algorithm to it. And there are many, many different types of agents, both virtual and real. So here is an example. Does anyone here actually have a Roomba? I don't have one. I've never used one. I don't know how good they are. But this is an agent, right? It's solving a problem, and that problem is the floor is dirty. Make it a little bit less dirty. I've seen some videos online where, like, maybe there's like your dog had an accident on the floor, and then the Roomba takes it all around the floor. But for the most part, they make, the problem it's trying to solve, it's to make the environment less dirty. And the environment is the physical world in this case. Here's another example of an agent. This is Spot by Boston Dynamics. It's been very popular in the news over the last few years for being able to solve pretty complex real-world problems. Of course, we're not going to get into anything this complex in this course, but it's just an example of a cool problem-solving agent. Here's another type of agent. This problem is called the cart balancing problem. And so what you have here is, let's see if I can get something here. So you've got something that you're trying to balance, and of course, in order to balance it, it's going to start to fall, so you're going to need to move it left to right. That's a 3D problem. This is a 2D problem, and so your actions are move left and right, and the goal here is to keep the pole balanced for as long as possible. So the agent here, with the actions of move left and move right, that would be the agent in this problem-solving environment. Here, if you want to play the game of chess, then the agent would be the player, right? And the interesting thing here is you may say, well, maybe the piece is the agent, is the player the agent, is the board the agent, and it really does depend on the problem, right? So for example, over here on the left, maybe we're writing an AI that plays Super Mario Brothers, and so the agent there would be Mario. But over here, maybe the player is Mega Man, and we're writing the AI for the dragon, right? In which case the dragon would be the agent. And so the agent depends on the context of the problem always. If there's one type of problem, maybe the agent is one thing in the environment. If it's another type of problem, maybe it's another thing. And so an agent within an environment will take actions to achieve a particular goal. So all these things in red, they're important definitions, right? And so the agent is going to perceive its environment somehow and then make a decision about which action to take in order to best achieve its goal. And in most cases, we are going to have to give the agent its goal, right? You can't just put a robot there and expect it to just decide what to do. We've got to give it, okay, I want you to get to that door as fast as possible or clean the floor or something like that. So we typically give the agent its goal and then place it within an environment. The agent takes its actions. Those actions usually make some sort of change within the environment, and then that process repeats, okay? And so artificial intelligence, one other definition we can throw in there, is the algorithmic discipline of making these decisions more intelligent. So how to go from my goal to the actions that I should take to achieve that goal. So what we have here, we have an environment, and then we have an agent. Typically the agent is like living within the environment, but this diagram doesn't necessarily show that. The agent is going to take an action. That action is going to affect the environment somehow, and then the environment is going to be perceived by the agent. It's going to make some sort of observation, and it's going to say, maybe in one case, it'll say, how close am I to my goal? So maybe I should take a different action. In another one, maybe I get a reward if I'm doing reinforcement learning or something like that, and then I'll take a different action based on the reward that I got. But this is the basic cycle, just like life, right? You're here, you're in this environment, you take some sort of action, the environment responds. Maybe the response is, now I'm here, right? Maybe it has a bigger response, like if I threw some water at you, you'd probably all move, right? So the response that the environment has, on a chessboard, it might be just a piece moving, maybe you've captured a piece, something like that. So the environment has some response, and then the agent has to perceive the new state of the environment and then say, okay, what has changed? What do I need to do now that it's different than it was? So the agent is going to perceive its environment through some sort of sensors. So for example, if you have a robot, maybe you have a camera, you have a laser, you have sonar, some way of detecting how far things are away, etc. Humans, we have our 5 main senses. I can touch the thing. I can shout to say, okay, everybody move, there's a fire or something like that. I can see, etc. In games, however, and in computer programs and simulations, This is a little bit different. Obviously, we don't have a physical laser that you're shooting around inside the computer. You don't have physical senses. And so you're going to have to make some sort of decision based on the environment, based on the problem. What senses do you give that agent, right? So that could be maybe keyboard input. It can detect what keyboard buttons are pressed. Or maybe it can read all of RAM, right? You've just given it all access to the simulation. Or maybe you've given it the entire game state, right? So for example, let's say we're playing a game of chess. Maybe we just have an array with all the pieces on it, right? In which case that is a perfect perception of the environment. But if we're outside and, I want to drive a car with a robot, maybe it can't see some things in the environment, right? So how it sees the environment is really important. And then after it's perceived the environment, it's going to decide what to do, and then it's going to act on its environment through actuators. And the actuators are the physical things that let it interact with the environment. And so, for example, robots might have wheels or tracks or arms. Humans, we have limbs. We have a stick that we can, do something with. In the game, maybe we move a piece on a chessboard or tell Mario to run to the left or something like that. These are all different. And we also, the agents may have some knowledge about the environment. We're going to talk more about knowledge in the future, but we may give them some knowledge. Like if it's a robot, maybe, okay, if it's white on the ground, it might mean it's slippery, something like that, some knowledge that we give the agent. Or the door is brown, or the stop sign is red. That's knowledge that we give the agent to help it make decisions. And agents, okay, more definitions. So a percept is an agent's perceptual inputs at any instant. And so it's the agent's current belief of the world. And the thing that we're going to be using for the rest of the course, we're not going to talk about percepts anymore, because that's just how it observes it. But the important part is that's the environment's current state. And so typically what we do whenever we're doing any sort of AI is we'll have a state of an environment. That's like taking a picture of the environment that we're then going to make a decision on. So if you're talking about a chessboard, that isn't so bad, because the chessboard isn't going to change until I've made a move, right? But if you're talking about a self-driving car, well, you better make a decision pretty quick based on that snapshot, right? Because you've got to drive, maybe you've got to avoid something or take a new image. So how often we observe states in the environment is also a big problem. Like how do we capture that information? How often do we process it? But in this course, we're not so worried about that. This is more of an algorithms course, so we'll be dealing with these environments that sort of don't change until we act on them. So really simple games. But the important part here is that it's an instantaneous snapshot of the environment. That is a state of the environment. If the state changes at all, it's a new state. Okay, so for all intents and purposes, states are immutable, and if anything changes, that is considered a completely new state. Even if it's 1 second from now or 1 millisecond from now, it's still a new state. A percept sequence, then, is the complete history of everything that the agent has ever perceived so far since the beginning of its training or its decision-making process, right? So maybe I started the robot over here and it's wandered and now it's over there. Does it have the full history of everything that it's ever done and everything that it's ever seen? That's actually an important question to ask. So, in general, an agent's choice of action at any given instant can depend on the entire percept sequence to date. So what I did in the past actually matters, okay? But in this course, we're only going to be looking at problems where the current state is sufficient to decide on the action that we should take. And so this means we're also going to have fully observable states. I'll talk about what that means in a second. And no state history is going to be required for this problem. You can talk about problems where you kind of get around this by encoding the state history within the state, but that's basically just the state history in another form, right? But in this course, it's going to be games, and environments like chess, like pathfinding, where I don't need to know where I've, all the sequence of everything that I've ever done in order to make the best move going forward. The agent's behavior is going to be given by the agent function that maps the percept sequence to an action. And that's just a fancy way of saying, given what I've seen so far, this is the action that I should do. And so right now, this is sort of a black box function. It's just called function agent. And you pass in the history of all the states, and then it does some magic, and it produces the action that you should do at the current state. So that's the agent function. And that's basically what AI is coding an agent function. You know, it could be a neural network, could be a search algorithm, could be a dictionary lookup, could be an if statement. Whatever that is, it goes in the agent function in this particular definition. And by the way, these definitions are the ones that are used by the optional textbook. Russell and Norvig, I think it is, the artificial intelligence. So that's why I use these definitions. So here's an example. Here's a state of an environment. Put your hand up if you can tell me what will change about the state in about a half second from there. Yep.
The person's orientation.
Okay, where will they be?
They'll be closer to the water.
How do you know that?
I guess from contextual knowledge.
What's that knowledge?
That they're being affected by gravity and then they're falling back.
Okay, so lots of knowledge there, right? To take that instantaneous snapshot and then say where they will be. And so if we're making a robot that's like a firefighter holding a blanket or something trying to catch this person, that's a lot of information that we don't have. What if this person, now, I mean, okay, you can see the ground there, so that's good contextual information. They're probably heading down, but what if there is a trampoline that you can't see and they're actually on their way up? Maybe they're in the middle of a flip, right? You don't know this for sure. And so if we were trying to solve the problem of like catch that person, you would definitely need to know more about the current state than right here. Now you may also think, okay, they probably jumped from right here. Well, what if they jumped from 30 meters up? Then they're probably going, you don't know this is Earth, right? There's a lot of assumptions here. And so in this particular problem, we would want to know something like this. Like you can pretty well say that, okay, that's not going from bottom to top. Like this person obviously jumped from the top here and now is heading downwards, right? So if we had right here, for example, this person, we could probably assign like, okay, here's the person's approximate center of mass, and then we could figure out the velocity to the left and then maybe position something to catch them. So in this particular case, what this is all trying to say is, in general, for the most difficult problems, you do need the entire state history. But for some problems, you don't. And chess is one of those problems. No matter how complex the board, if you walk into any game of chess that's currently in play, you can derive the best move to do at that particular state without having seen any of the other actions that are in that game. Now, okay, there's a small technicality there where there's something in chess where if you repeat the same move like a number of times, it's a draw. Throw that out the window for a second. Maybe somewhere is written down the number of moves that have been repeated or whatever. But for the most part, 99.999% of chess games, you can just look at the game state and then say the best action to do. So the history of that chess game is not required in order to make the optimal action. Now, in some cases, let's say you're playing poker, for example, there's some games where if you know how the opponent has acted, it could possibly lead to you being able to exploit that opponent in the future. Like, for example, if I just watch them play 20 hands of poker and they always raise every hand, that's important information to know to exploit that person. But that's only to exploit that particular person. It does not help you in making the optimal decision because the optimal decision does not involve anything that person has ever done. It only involves the properties of the game. We'll get into that more later. This is an interesting example. This is from the game League of Legends. Hopefully, so what's happening here is that it's a team of 5 players versus another team of 5 players. And this is an important objective in the game. This is called the Baron. And this Baron is currently being killed by this team, this blue team down here. And the way the game works is that the team who deals the last hit point of damage to that enemy gets a huge bonus. They get a ton of gold, they get a buff that regens their hit points, their spells cast faster, all sorts of great stuff. So it's very important to kill that, right? And what you don't want is a situation where you're killing it and then the other team is able to come in and just deal the last hit point of damage and steal it away from you. But that's what happens here. So you see them killing it, it gets very, very low, and then this player from the other team just comes and shoots one bullet at the exact perfect time and kills it and steals it from them. And this was huge. This completely swayed the entire game. However, you may say, okay, well, that seems pretty easy. You just walk up and fire a bullet, like this person did. But here is what that person actually saw as they fired that bullet. They couldn't actually see what was happening, right? They fired it blind. Now, that's blind to the instantaneous current state. But what they did see was probably about 30 seconds ago, the other team walking into the Baron pit and start fighting it. So through their game knowledge, they approximately know, okay, they have these characters with these items, so probably in about 20 seconds, it'll be close enough to dead that I can fire a bullet and hopefully steal it. Now, this person is not like a god. They can't see everything. They can't do this perfectly. And 9 times out of 10, probably 99 times out of 100, it won't happen, right? Like they won't actually steal it. But this is a case where it did. And the only reason I'm talking about this is because this is a case where that person needed to have an insane amount of game knowledge in his agent function, which is his brain, and also needed to know the state history up to that point, right? All that stuff that had happened in the last minute or so was all very important to making that decision. So in general, you do need to know it. But we're not solving League of Legends or Dota or any of those complex games in this course. Okay, so let's talk about actions. An action taken by an agent in a given state transitions the state to another state. Now, sometimes the transition will lead you to a state that is drastically different. For example, in chess, you could be losing at one state and win the game at the next state, right? You go from not checkmate to checkmate. That's a pretty dramatic. You could go from alive to dead in a video game. Or you could actually take the action of doing nothing and just let the game world progress a little bit. So the effects of actions can be dramatically different, but an action does take one state from one state to another state. And here's the simplest possible example where you can represent your entire environment in a state transition table. Okay, so here my environment just has 2 states. If you've got an environment with 1 state, it's really not that interesting, right? You can't really do much. So I've got state 1 here, and I've got state 2 here. And so this right here is blatantly taken from Wikipedia. It's a pretty good example, right, for educational purposes. But we've got state 1 here and state 2 here. This state transition table says that if I'm in state 1 and I take action 1, then I stay in state 1. If I had taken action 0, then I would move from state 1 to state 2. Down here, if I'm in state 2 and I take action 1, I stay in state 2. Otherwise, I go to state 1. So what this basically says from reading this state transition table is that if I take the action 1, whatever that means, then I stay at the same state. If I take action 0, I go to the other state, right? And so over here, we can see this graphically where I have state 1, and I take action 1, and it leads me back to the same state. And even though this has like distance, it doesn't mean that this action takes longer, right? It's just an instantaneous transition to the next state. So action 1 is going to keep us in state 2, but action 0 is going to take us from one state to another state. And so this is just, you've probably all seen this before, but just the definition of an action just takes us from one state to another state. And this is done by the state transition function. Call this STF. This is also called a successor function. It could also be a table, as we saw over here. So this state transition function, a function is sort of a superset of table, right? So a table could be how it actually accomplishes the function. It could be a graph, could be any number of different things, but it's an arbitrary function in general. And what it does is you take a state S, that's the current state, and an action A that you've decided to perform, and you pass S and A into the state transition function, and out pops S prime, which is the next state. So throughout the course, if you see something with a prime on it, it usually denotes the next thing. Okay, so S prime is the next state, A prime is the next action, etc. So let's look at some examples of actions. Here's an action, right? You do some jumping jacks, it takes you from a less healthy state to a more healthy state, right? So you can think of all sorts of physical actions that you can do in the real world that have an effect on you or the environment. Here's an example of an action that we'll be doing in assignment 3. This is a game called Connect 4. It's a board game which is actually played vertically, and what you do is you drop pieces in from the top. And so if this is the current state of the game, and you decide to put an action in, or a piece in this column, you take this action, and now it goes all the way down to the bottom, and here it is. So that's an action in this particular board game. Here's an action in another video game. I'm just going to hold right on the controller. That's the input to this system, and then the state transition function would be the video game's game mechanics, or whatever. And so if I'm holding right here, Mario's walking to the right. That's the effect of that action. An action in a chess game, just moving a piece, right? Those are the different actions that you take in chess. And we'll talk about things like legal actions. What is a legal action? What is not a legal action? And the actions that you can do at a particular state may or may not be legal depending on the state itself. So for example, in Super Mario Brothers, you can always hold any direction. That's always a legal action, right? But in a game of chess, whether or not you can move a specific piece to a specific place on the board will be legal whether or not, other pieces are in that spot, etc. Here we have fighting games, this is Street Fighter, lots of different actions in that game. And if you slow this down, right, the game is operating at about 60 frames per second. And so if you slow it down to like 16 milliseconds per action, then the person's controller inputs at any given 16 millisecond window is the action, the particular single action that we're talking about here. Okay, so those are actions. I think those are pretty intuitive. Policies. A policy is something that maps states to actions. And so it basically says, if I give you a state, what is the action that I should do at that state? Now, it doesn't mean that it's the best policy. It just means that it is a policy. For example, there is a policy which says always do nothing, right? So I could stand here and do nothing, and that could be a policy. It would be a policy, always run as fast as you can. That's a different policy. So this is supposed to be the Greek symbol pi. It's just that this font in LaTeX didn't let me type it. So policy pi. If we have an optimal policy, meaning that it takes the action which most quickly leads us to our goal, then that's called pi star. And so pi star, if we see a star in the course, it usually means that it's the optimal thing to do, except for the A star algorithm. So we'll be seeing things like H star, that's the optimal heuristic, C star is the optimal cost, pi star is the optimal policy. And so pi of S is a function. In general, your policy is a function. That could, again, it could be a table, it could be a neural net, it could be an if statement, doesn't really matter, it's just a function. And it says, given that we are in state S, do action A. That's what a policy does. A policy could be implemented, like I said, as a lookup table, a bunch of if statements, an arbitrary function calculation, a deep neural network, it could be whatever it is. As long as it takes in a state and produces an action, we can call it a policy. Here is an example of a policy. This is a policy for an environment in which we want to do pathfinding in a grid. So this will actually be very close to one of the assignments in the course. And so we've got an agent here that is currently this red circle. And its goal is to get to one of these green locations as quickly as possible. It can move up, down, left, or right. And these dark gray tiles here, they're walls. So you can't move through the walls. And so what this is a visualization of a policy that says, for example, if you want to get from here to the closest green tile, move to the right. So it's pointing to the right. Then to the right, then to the right, then down, down, left, left, left. Over here, for example, it says move in any of the 4 directions. Why is that? Well, it turns out that if you move in any of the 4 directions, the length of the path to the nearest green tile will be the same, right? So this is one example of a policy where, given that you are in a particular state of the environment, and for this case, the state of the environment is which grid cell the agent is on, it will tell you the action to do. Here it's a very simple table, but not all problems are that simple. This is another example. Who here has ever played blackjack before? Or knows the rules to blackjack? One person. You're all so sweet and innocent. Okay, so blackjack, which I will be talking about later because it's a good example, for reinforcement learning. It's a card game that you play in a casino. You play it against the casino. You don't play it against other people. And so the casino gives you cards, and then you make some actions. Your actions are, I want another card, or I don't want another card, basically. And what this table shows you is that if you have those cards, and the dealer has those cards, look it up the cell, and that's the optimal action that you should take. So blackjack is a solved game, and it's provably solved to the point where you can statistically show that you're always going to lose 2% of your money over time if you play optimally, yet people still walk into the casino and play that game, right? It's the idiot tax. Now, I mean, it's fun, so maybe you're willing to pay 2% of your money over time to, have a drink and play with friends or something like that. But it is a losing game, and anyone who ever tells you that they have a system to beat it, it doesn't exist because the casino's still open, right? And so anyway, we'll talk more a little bit about gambling later because it's an interesting statistical problem. So that is another example of a tabular policy. Tabular meaning you can put it in a table. This is a flowchart. Flowchart is also a policy. So let's have a look at this one over here. Start of the flowchart, alarm rings. Are you ready to get up? No. Hit the snooze button. Delay, alarm rings again. That was me this morning. I think I hit my snooze button like 7 times. And I don't even remember it. It's crazy. Then you're ready to get up. Yes. Okay, climb out of bed. Here's another one. You can apply this to all your life's problems, right? Do you have a problem? Yes. Can you do something about it? No. Then don't worry. If you can't do anything, then why would you worry? And if you can do something, then do it and don't worry, right? And if you don't have a problem, then don't worry. We could solve all the world's problems with that one flowchart. Right? Yeah. Don't worry, be happy. So that's another example of a policy. You can implement it in a flowchart. And how would you implement a flowchart in code? If statements, right? If this, then that. And so if statements are still AI. They're just not as academically interesting as other forms of AI. Here's another definition. Rationality. Rationality is really interesting. A rational agent is one that does the optimal action for every possible state. However, very importantly, the optimal action is the one that makes the agent most successful. And so what does that mean? Well, we must define some sort of performance measure in order to define success, right? How well am I doing? I don't know. Nobody told me what I'm supposed to be doing. So we need a performance measure. And the rational agent has an optimal policy within its level of knowledge. Okay? There are some times you don't have all the knowledge, right? You might not know the outcome of some randomness. You might not know that there's an idiot in a car 2 cars ahead that's about to slam into you, right? Just because you failed does not necessarily mean that you made a suboptimal decision, right? You play sports. You went for the goal. You had a 90% chance of getting it, but you didn't get it. It's still the optimal play. I get so frustrated at sports, especially like American football, because it's like, oh, the quarterback threw this pass 70 yards that had a 1% chance of working out because it was so difficult, but the guy caught it and they won the game. What a hero. He's an idiot. He just happened to get lucky, right? And the person who made the play that will work 50% of the time, who happened to get unlucky that time, well, they get fired, right? The world seems to look at the outcome versus the actual rationality of the choice that was being made, right? Someone who goes and buys a lottery ticket will brag and wins, will brag to all their friends, see, I won $100. It was worth buying a lottery ticket. But no, it was still like the expected value of that was still not positive. We'll get more into that later. So a life lesson is to look at like the expected outcome, not necessarily the outcome that happened. Performance measure, then, is going to be very, very important. It's the criteria for success of an agent. It's also sometimes called the evaluation function, right? We're going to evaluate an agent, and that's the performance measure. So here's a typical scenario. You put an agent into an environment. The agent is going to perform a sequence of actions. The actions cause the environment to go through a sequence of states. If the sequence of states is desirable for whatever reason, then the agent has performed well, then the evaluation is higher. Okay? So, for example, games are often really easy Has anyone ever seen Flappy Bird before? It was a game that was out a few years ago. It was so successful, it was making the author of the game like $50,000 a day in ads. And he pulled it from the App Store because he was like so overwhelmed with the money and his... Anyway, it was crazy success. And all you do is press one button and bounce a bird. But anyway, that's another story. The criteria for success here is the score of the game, right? Lots of games have a score. And the criteria here is move to the right. So if you get further to the right than I got, then you beat me, right? If you get the high score, that's just going to the right. That is the easiest possible criteria for success, move to the right. That's how a lot of video games operate. If you have a problem like pathfinding, for example, we've all used Google Maps. One of the possible ways of defining success here would be shortest distance, right? So I want to get from point A to point B in the shortest distance possible. But that's not always the only measure that you would use for pathfinding. Maybe we want shortest time possible, right? If I can get on the highway, maybe I've gone more distance, but I've done it faster. Maybe if I take a different route with less traffic, so there was this really famous problem where it was either UPS or FedEx or one of these big companies who decided to look at optimizing their gas usage, right? Because fuel is really expensive. It's majority of their operating costs. So what they did was they found that a lot of their trucks, when they got to an intersection, they wanted to turn left. They were spending a lot of time stopped, idling, burning gas while they were turning left. And so in some places they found that instead of turning left, if they did 3 right turns that they didn't have to wait for, they would use less fuel. And I think they saved like 7 to 10% of fuel in some cities by making 3 right turns instead of one left turn. So it's really interesting how you define it. So one of your, maybe you're really environmentally conscious and your criteria for success is gas usage getting from point A to B, or monetary cost getting from point A to B, right? So there's all sorts of different criteria for success we could use even in the same environment, right? So it's a choice that you have to make. In the cart balancing problem, it's just the amount of time that you were able to balance the thing, right? The longer, the better. In a lot of games, who here plays chess or at least knows the rules of chess, right? So, okay, most people have played chess. So when you're playing chess, if you look at, maybe, a world champion can look at that board and say who's winning, right? Because they've played so many games. But me, as a very bad chess player, like definitely below anyone who plays regularly. I play maybe like 2 games a year. So one thing that some people do is assign points to the pieces on the board, right? So some people say, okay, one way of knowing if you're winning or not is that the pawns are worth 1, rooks are worth 5, queen is worth 9, bishops are worth 3, whatever the formula is, add up your pieces and add up their pieces, and then that's a good measure to tell if you're winning or not, right? However, that's still not a perfect measure because you could be winning by 20 points, but it turns out they had just sacrificed their queen to put you in checkmate on the next move, right? Really, in most games like this, the only real performance measure is whether or not you won the game. It's right at the end of the game. Did you win or did you lose? And the problem with that is that it's so far away sometimes. How do I know if I'm currently doing well or I'm currently not doing well? That's something that we'll come back to when we talk about two-player search. So there's the performance measure, which is win or lose. It's like the hard and fast optimization problem of least distance. But we may also see in the future, because it's so far into the future, to know if I've won or lost, we may have these sort of intermediate performance measures. We'll call them heuristic evaluation functions. They're not exact, but they may help us get toward our goal. That'll be later on assignment 3. Okay, so rationality is going to depend on 4 things. The performance measure that defines success, the agent's prior knowledge of the environment, the actions that the agent could perform, and the agent's percept sequence. Rationality is different from omniscience. Okay, so rationality is one thing. Rationality, again, is making the best decision based on what you know. Omniscience is sort of like if you were the programmer of the simulation, or the God of the universe, who could know everything. Not only where everything was, but let's say, for example, if you want to deal a card or roll a dice, what the outcome of that would be beforehand, right? So an omniscient agent is going to know the exact outcomes of actions, the exact outcome of randomness, and knows the entire state of the environment. So here's an example. Let's say I have a 6-sided die, okay, just a normal die. And I tell you, okay, I'm going to bet you $100. If it rolls between a 1 and a 5, you win $100. If it rolls a 6, I win $100. Who here would take that bet? Right? Only 3 of you. Come on, it's a 5 and 6 chance, right? So you have a 5 out of 6 chance of winning $100. I have a 1 out of 6 chance of winning $100. Unless the small possibility of you losing would dramatically affect your financial status, right? Maybe you're on your way to pay your last month's rent with that $100, so you absolutely can't use it. But that is a positive expected value. We'll talk about expected value later. But it means if you keep doing that over and over, on average, you'll win a lot of money, right? I'm not saying gambling is good, but that's a good bet. But in this particular instance, you got unlucky, right? Was the bet still rational? Yes, it was still rational because you had a 5 out of 6 chance of winning it, positive expected value. But an omniscient agent would not have taken that bet because it knew that a 6 was going to come up, right? And so this oracle, omniscient, godly agent who did not take the bet, it's because they knew more than a rational agent could ever know, okay? So just realize here, the point I'm trying to drive home is that the omniscient agent will always have the best outcome, but the rational agent is going to take the action that will lead to the best outcome on average, usually, right? All right, so those are agents. Now we'll talk more about environments. I'm sure you can all get you all know what an environment is, basically where the agent is, but there are a lot of theoretical properties of environments that we're going to want to talk about and regurgitate on exams. So, a task environment is essentially the problem that you're trying to solve, right? It defines everything that makes the problem interesting. A rational agent is going to be the solution to that problem. So, the specification and properties of an environment greatly impact the design of a rational agent to act within it. And the reason for that is specific properties of an environment actually define which algorithms we can or cannot use in that environment. For example, certain algorithms do not work if you cannot see the entire environment. Certain algorithms do not work if you have randomness in the environment, right? So you've got to know these theoretical properties. If you're working for some company and your boss sits down and says, I need an algorithm that makes a decision here, the first thing you need to do before you go on ChatGPT and ask it to solve it for you is identify the properties of the environment so that you know the algorithm at least has a chance of solving the problem. And again, a state is a particular configuration of a given environment. So let's look at the easiest, the canonical example here. Our environment is chess. So you want to make a chess-playing program, chess-playing AI. The environment of chess has a board over here, and it has different pieces. So, you list out the different pieces, you list out the board size, whatever. It also has the rules and the boundaries. So, for example, pawns can only capture on a diagonal, rooks can go as far as they want in a straight line, up or down, bishops can move on a diagonal, etc. So those are the legal actions. It defines the starting state of the game. So you have to put your pieces in a particular configuration to start the game. It also defines the goal configuration or state of the board, right? So over here, you have the starting state of a game of chess. And after you've played a bunch of moves, here is some random state of chess after some amount of moves, right? And it said here the goal condition or goal state. The goal state of a game of chess ideally is to win in a position where your opponent has been checkmated, right? So their king is in check and they have no legal moves to take them out of check. So that would be a function. You would have to apply a function to this state to determine whether or not that's the goal state. In other simpler examples, let's say you're doing pathfinding. I want to get from here to the Avalon Mall parking lot, right? You don't need a function for that. You just have a list of states. Am I in the Avalon Mall parking lot? Yes. So that is the goal state there. So the goal state check can be an arbitrarily complex function as well. So agent observations of the state. So for the agent, the state of the environment is based on the observations you have allowed it to make. That observation may not be a complete representation of the environment's actual state, right? So there's the actual state of this room, and then there's what I can see of the room, right? I don't know if 3/4 of you have pants on, because I can't see below the seats, right? Maybe some of you have purple pants, maybe some have white pants, maybe some of you are wearing shorts, right? Hopefully you all have pants on, but like I can't see that. So there's part of the environment I can't see, but it is still a part of the environment. But the state is from the agent's point of view, and it's how it makes decisions. The agent's observations, which are the state, is all that it can actually use to make a decision. So in the game of chess, the agent can observe the entire environment. There's nothing secret about the game of chess. Tell me, someone put up their hand and tell me a game where you don't have complete information of the environment. Yep. RPGs? What can't you see?
You haven't explored the whole map. You started out just now.
Yep. So that's, yes, that is true. What about like a simpler board game or other game that you can play like without electronics? I guarantee that you have all played one. Just put up your hand because I don't know who's talking. Put up your hand before you say, yep. Okay, so what can't you see in Monopoly? It's true, but... So, Monopoly has a property that's shared any card game. If you're playing cards, you can't see what's in the other person's hand, right? Okay, in Monopoly, there's piles of cards that you can't see. And so that's one of the things in Monopoly. Did you have another example?
Yeah, I wanted to say Uno, but that's...
Yeah, any card game basically, right? Almost every card game has hidden information from one person, okay? So, other examples, driving. You can see a lot of the environment when driving, but if you have your driver's license, you know what a blind spot is, for example. You have to look. You can't just rely on your mirrors. There is a blind spot where your mirrors don't check. You can't see that. You can't see, you've ever, beeped at the person in front of you. Why are they going so slow? Well, maybe you don't see the chicken crossing the road in front of the car, right? There'll always be something in the real world that you can't see. And so this is a hard problem because of that. So that's one property. The level of observability of the environment. Certain algorithms may or may not work because of that. Let's talk a bit about the state and action spaces. What does that mean? The state space is the number of possible configurations of the environment for a given problem. So how many different states are there? You just count them. The action space is the number of actions that are possible from a given state. So this is usually given as a worst case in terms of actions because many different environments will have a different amount of legal actions based on the state. And so this is used as an estimation of complexity, right? So for example, let's say, your boss at some company or your supervisor comes to you and says, we want to solve this problem. The first thing you should do, look at the properties of the environment, one of them being the state and action space. And if the state space is under a few trillion, it means that you can probably just write an algorithm to enumerate every possible state and pick the best action, right? So it's used as an estimation of complexity. Let's look at an example. So, tic-tac-toe. Hopefully everyone here knows the rules to tic-tac-toe, also called noughts and crosses in the UK. So in tic-tac-toe, you've got this board. I'm going to choose to put an X or an O in any one of these given spaces. And so there are 9 possible spaces. At each of the possible spaces, there are 3 possible pieces that I can put there. This animation plays way too fast for this. But let me go back and then forward again. All right, so there's 3 possible things I can do. There's an X, an O, or a blank, because I haven't put anything there yet. and there are 9 possible spaces. So there are 3 to the 9. That is the state space, whatever that number happens to be. Okay? That is the number of possible states of a game of tic-tac-toe. Now, if you went to actually solve the game of tic-tac-toe, you would very quickly, as an educated computer scientist, realize that some of those states are the same state, but like rotated. Right? So if you place an X in the top left, that's essentially the same start as putting it in the top right. And so there are ways, those are called like symmetries in the game. So let's just take symmetries and we'll remove them for now, because it just makes the problem a little bit easier. But your boss has come to you and said, can we write a perfect tic-tac-toe playing program? And you look, wow, there's only like 10,000 possible states or less. So yes, I can very easily just enumerate all the possible things you can do in tic-tac-toe and create a perfect AI for that. You can solve tic-tac-toe easily. Okay, your boss comes back the next day. You did tic-tac-toe. That's awesome. Can you do chess? Well, let's do the analysis. There's 64 spaces on the board, 32 empty spaces. There are 8 pawns in 2 different sets. That's the ways you can place 2 pawns. There's a lot of combinatorics going on that I'm not going to go into detail with. And so that's 10 to the power of 42, right? 10 to the 43. That's the number of states of chess. So you go back to your boss and say, do you have a computer that can do 10 to the 43 calculations in a reasonable amount of time? And they'll say, okay, here's $3,000 budget. And you'll say, okay, well, you can't, right? So chess is not a game which you can enumerate all the possible states and just choose the best action. It's way too big. What's that? 1,000 times 1,000 times 1,000 times 1,000. So it's a lot, right? A billion billions or something like that. Then, okay, they come to you and they say, go, the board game. Let's have a look. Each space on the board can have 3 values, just like tic-tac-toe. Okay, we're starting out pretty well. Uh-oh. There's 19 rows and 19 columns, and there's 361 possible places we can put it, right? So there's 3 to the 361, which is, yeah, the number is so big that it doesn't even matter anymore. So we cannot enumerate all the possible states of a game like Go and find the best solution. Okay, so what that says is it doesn't mean that the game is complex. It means that it's a sort of measure of complexity that shows you can't just trivially solve it via brute force. Okay? So the state space complexity of tic-tac-toe, some people like to just write the number, right, the exponent. So it's 4, around 10,000 for tic-tac-toe, 43, 10 tredecillion, whatever that means for chess, and then this made-up number over here for Go, right? Really, really big. So that's the number of possible configurations of the board for those games. Now, there's another thing, which is game tree complexity. If state space complexity is the number of configurations of an environment, then game tree complexity is the number of ways to take a sequence of actions through the game. So some states may be able to be reached via many different sequences of actions. Okay? So let's have a look over here in a game of chess. This is just a couple of moves into a game of chess. Here is a state. This is one state of the game of chess. Now, how many different ways could I have gotten to this state of chess? Well, if white moves first, they could have moved their right knight first, right? So they could have done this one, then this person could have done this one, and then I could have done that one, and then they could have done that one. So it's basically all the possible permutations of the ways we could have taken these turns. But now, make this a much more elaborate, so maybe there's like less than 10, but some number of ways to get to that particular state. Now you take like a mid-game position of chess. There are almost infinite ways that you could have gotten to that particular state of the game of chess, right? Especially the fact that you can like move and then move back and move back. So there could literally be an infinite, actually there are an infinite number of ways we could have gotten to that state because I could just keep moving my piece back and forth. But it's just the difference between the number of ways to get to a state, the number of possible plays through of a game, and the number of possible configurations. Similarly, for tic-tac-toe, I could have placed my X here first or my X here first, right? You can get to states many, many different ways. And so if we have this value for the number of states, then the numbers for the number of ways to get to those states is going to be a lot bigger. And so this, the numbers now are so big we can't even think of them. But actually, let's think of them. Because 10 to the power of 360, if there's something that humans are bad at, it's thinking about big numbers. Okay? People sometimes talk about billionaires, right? How much money does a billionaire have? It's shockingly difficult to think about how much money $1 billion is. Here's my favorite quote when it comes to billionaires. What's the difference between $1 billion and $1 million? The answer is $1 billion. Right? It's the difference between 1 million and 1,000. $1 million is as nothing compared to 1 billion as 1,000 is to 1 million. And so it's very difficult for us to conceptualize these numbers and just really how big they are. But here's a cool little thing that I saw online. Here's the number of seconds in a century. This is more seconds than any of us has left to live. Maybe there's some, maybe we're all immortal eventually, who knows. That's the seconds in a century. This is the number of total humans born ever. This is the age of the universe in seconds, right? Look at how powerful exponentials are. In 100 years, which is nothing, that's 9, but the age of the universe, which is billions of years, is 17. You don't even double that number and you get the age of the universe. So exponentials are just crazy, right? Here's the diameter of the universe in meters, estimate. Here's the number of stars in the universe. 10 to the 80 is the number of atoms in the universe, approximately. And 10 to the 122 is the number of protons needed to fill the universe, right? Not the number of protons in the universe, but in order to 100% fill all the space in the universe with protons. And then here's Go's game tree complexity. Right? So this, if you had a supercomputer in every proton that filled the universe, you'd still need a universe to the power of the universe amount of time to compute this. It's insane, right? You can't even think about how big these numbers are. And then StarCraft is 10 to the 1,000 to the 1,000. Video games have so many states. It's just crazy. I won't even get into it. Basically, the numbers are so big that it doesn't matter. But here's the important thing. A large state space does not prove that a game is complex. It can prove that a game is not complex, because if it only has 10,000 states, you can just solve it. So it's not complex, right? Might be hard for a human to reason about those type of games, but a computer can solve it instantaneously. But just because something has a large state space does not mean that the game cannot be solved. Solved trivially, even. So let's think about this. Consider the game of Go. So in the game of Go, let me go back to the board of Go. Okay? So here in Go, you've got a board, and you've got 19 times 19, 281 or something. What was it? I can't remember. But it's a big number. And so I put a piece down, then you put a piece down, then I put a piece down, then you put a piece down. One person has black stones, one person has white stones. If you surround the pieces of your opponent with stones, you capture those pieces and they come off the board. And at the end of the game, which comes when either one person has resigned or there are no places left to put stones, the person with the most stones remaining on the board wins. It is extremely complex, and you can't just enumerate all the things to solve it. However, think about the game of Go. If we eliminate capturing, then what happens? It's still got the exact same complexity. There's still the same number of actions. There's still the same number of states. There's still the same number of ways to go through the board. But if you can't capture any pieces, and there's an odd number of squares on the board, whoever goes first wins. And it doesn't matter where you place your piece. Because if there's an odd number of places, consider there's 3 places. I go, you go, I go. I win. Because I always make the first and last move. And so there's an odd number of places on the board. Doesn't matter where any of us place any of our stones. It's trivially solvable by moving anywhere, and player 1 always wins. Okay? But it still has that same insane complexity. So the test for complexity here doesn't prove it's complex. It can only prove that it's not complex. But it's a good first step to tell you what type of algorithm you may want to apply. right? Because if you can just trivially solve it, you don't need to think about any strategy or call a bunch of experts and pay them for consulting time. You just solve the game right away. So it does show us the computational complexity required to solve the game via exhaustive search. And I'll look at this. I had a slide here already. So tic-tac-toe, solve it. Just write a program, a few lines of Python, have it out the door in an hour, right? No problem. Go, call up Google, right? So, okay. So let's talk about defining an environment. Oh, geez, I'm going so slow. I've got to start going faster. So I apologize for going faster. The environment definition is the rules and dynamics that government, the physics, the game rules, etc., the legal actions allowed at every state, the initial or goal state, that's usually given by the problem instance, which we'll talk about next class. And environments have several properties, and I've got 14 minutes to get through these properties. The first property is fully versus partially observable. We've already talked about this one. In a fully observable environment, the agent's sensors give it access to the complete state of the environment at any given time, and access to the relevant part of the state for actions. In games, these are called perfect information games. You have all of the information. In partially observable games, data is hidden or occluded, or your sensors might be noisy or have some randomness. They are called imperfect information games. So, chess, perfect information game. Video game, like you said, RPG, or real-time strategy game. Card game, imperfect information. You can't see everything. Property number 2, deterministic versus stochastic. In a deterministic game, the next state of the environment is entirely determined by the current state and the action. There is no randomness in the environment. So no randomness is another way of saying that if I take an action, it will always have the same outcome. Okay? In a stochastic environment, which means non-deterministic, there is some uncertainty about the outcome of actions. So there might be a dice roll, a card draw, maybe you have a 20% chance of getting a critical hit, something like that. And there might be randomness due to the nature of the environment, etc. And you always think about that from the agent's point of view, which is if the agent takes an action, do they know for certain where they will be, what state they will be in? If no, then it's stochastic. If yes, then it's deterministic. And so, again, chess is just one of these environments that has nice properties. So it is deterministic versus dealing cards, rolling dice. That's stochastic. Next, we have episodic versus sequential. In an episodic problem, an agent's experiences are divided into atomic episodes. The agent perceives the current state and takes an action, and the next episode doesn't depend at all on the previous action. Episodic problems are not super interesting. We're going to be dealing with more sequential problems, where we have the current action influencing future decisions. So actions may have long-term consequences. So for example, if you're doing this problem we talked about last class of like optical character recognition, whatever the current character is doesn't matter what the next character is, right? They're independent atomic episodes. In chess, what I do on the first turn matters for what I do on the 10th turn, right? So it's a sequential problem. Next, we have dynamic versus static. In dynamic environments, the environment may change while the agent decides. So the environment is continuously asking what to do. Versus a static environment, the environment only changes when an agent takes an action. It doesn't matter how much time it takes to think. And so in games, we might talk about real-time games versus turn-based games, right? So a dynamic environment is something like the real world. Like if I'm standing in the road, I've got to make a decision because the car coming toward me or the train coming down the tracks is not about to like wait for me to make a decision. I've got to decide. Similarly, in a video game, the enemy might be coming at you. You have to make a decision. It's dynamic. It's not waiting for you to make a decision. Other games may wait for you to make a decision. Maybe like a pathfinding problem or a game of chess or something like that. And yes, you can add a timer to the game of chess, which would sort of make it dynamic. But we're talking about the, I move, then you move sort of property of the game of chess. Then there's discrete versus continuous. The distinction is applied to the state of the environment, and it determines basically the way that time is handled in the game. So discrete would be a finite number of distinct states that go through a sequence, like a game of chess again. You have a discrete set of percepts and actions, and continuous, you would have some sort of continuous time or actions. So discrete here, basically, any tabletop game. And actually computer games as well, because even though they look continuous, they're actually like discrete states that move just really fast, versus the actual real world would be the only real continuous environment that I know about, right, where things are happening at an infinitesimally small amount of time. So whether or not, the environment actually, the real world or the universe operates at discrete time steps or continuous time steps, I don't know, but it's continuous enough that it cannot be broken down. The only way we can think about it is breaking it down. So typically, because computers are discrete, the only way that we can work on these problems is defining a time step that we want to work with. So if I'm doing a self-driving car, I'm going to be wanting to make a decision every, let's say, millisecond. Or if I'm really bad, every second. Right? So you've got to choose an amount of time and say, okay, take a snapshot of the state, make an action. Take a snapshot of the state, make an action. So whether or not that's self-driving, which would have to be very fast, maybe something else wouldn't have to be so fast. Single agent versus multi-agent. In a single agent problem, we have one agent acting at a time. So for example, solving a crossword or a Sudoku puzzle or a pathfinding problem. In a multi-agent problem, we've got multiple agents acting together, either cooperatively or competitively. So for example, over here you have a single agent problem, which is just pathfinding. How do I get from here to here? Here we have a multi-agent problem, in which you have 10 agents, 5 cooperating against another 5 cooperating. So this is actually quite a complex environment in comparison. Complete versus incomplete information. This sounds a lot like perfect versus imperfect information, but it's actually different. In complete information environments, all of the game rules and physics are known, and all of the possible actions are known. Versus in incomplete information, the game rules or game physics may not actually be known, right? And so the actions may have to be discovered. So for example, as much as we know about the universe, we don't know exactly what will happen when we do something, right? Like, how hard do I have to blow for this to fall off the table, right? I don't know that. I might have to try it a few times. So there may be incomplete information. Or maybe you are put into a video game where you don't know the goal until you've reached it, right? You're not told any knowledge. So you don't know that you're playing chess. You don't know that you're playing checkers. Maybe you can just test actions and test the goal condition or whatever. So that's complete versus incomplete information. So what I've done here is put like a little table here where we kind of go from easiest problems to more challenging problems. So each of these properties sort of had two, one or the other, on or off, and one is basically less complex and the other is more complex. So we start up here at a sequential, single agent, deterministic, fully observable, static, discrete problem, which is something like a crossword puzzle, right? It's just you. There's no other agent trying to interact with you. You've got as much time in the world to solve it. It's one of the easier types of problem to work on. Then what we're going to do is we're going to change single agent to multi-agent. And now we've got a game like chess, right? So it's still sequential, multi-agent, but it's still deterministic, fully observable, static, and discrete. So now let's change deterministic to stochastic. That would be a game like backgammon, right? Or another game where you roll dice or play cards, something like that. Actually, not cards, because this is a fully observable game. So this is a fully observable game that has randomness in it. Next, let's take fully observable, change it into partially observable. So we have a game like poker, or a lot of card games, right? Where we have shuffling and dealing of the cards, so that's some randomness. We also have information that is hidden from us. But it's static. Like, I have to make a bet, and you have to make a bet. There's no train coming at me, right? And it's a discrete problem. And then we move up into video games by changing the static nature into a dynamic nature. So now the timing of your actions makes a big difference. And so you introduce this dynamic property, and you have games like StarCraft or other video games where there's also hidden information. And then you change discrete to continuous to sort of make it as hard as possible, and then you've got sort of real-world problems, right? Where you may have, now whether or not randomness actually exists in the real world, that's a whole other issue. Like, how do you generate randomness? How do you test for randomness, etc.? But there's this idea of randomness through lack of knowledge, right? Like, I can flip a coin, and because I don't know the exact state of the universe, and the exact simulator of the universe, then for all intents and purposes, for us, that coin flip is going to be random, right? The outcome of that, because I cannot predict it. So whether or not there is true randomness in the real world, there is for all intents and purposes of AI problem solving. So that would be sequential, multi-agent, stochastic, partially observable, dynamic, and continuous, the hardest type of problems. Now that doesn't mean that every real-world problem is harder than poker, or is harder than even a crossword puzzle, right? You may have a, guide this robot to that door. Super easy problem, but it's in a hard environment, right? It just means that there are properties of these environments that mean, like, the first algorithm that we use can't be applied to real-world problems. Or say the first algorithm we learn next week, you can't apply it to real-world problems because the properties don't match. So on an exam, what I might ask is, here's a game we've talked about, what are its properties? Or here are the properties, I want you to provide me with like an example environment like that. And that's it for this class.